Welcome to the SEI Podcast Series, a production of the Carnegie Mellon University Software Engineering Institute. The SEI is a federally funded research and development center sponsored by the U.S. Department of Defense. A transcript of today's podcast is posted on the SEI website at sei.cmu.edu/podcasts.
Welcome to the SEI Podcast Series. My name is Dr. Grace Lewis, and I'm a principal researcher at the Software Engineering Institute and the lead for SEI's Tactical and AI-Enabled Systems Initiative. Containers have become an expected part of software development pipelines. However, although container builds should be identical, containered images often differ because of external dependencies, therefore decreasing trust in containers and possibly hiding malware insertion. A recent SEI tool helps developers identify those differences. Today I am joined by two of my colleagues, Kevin Pitstick and Li-Han Zhan, both software engineers in SEI's Software Solutions Division. We are here to discuss a project that they are involved with that aims to improve container reproducibility. They've created an open source tool called Vessel that analyzes container builds to identify their differences, spot potential problems, and make containers more trustworthy. Welcome.
Thank you.
Thank you.
So before we get into container reproducibility, can you tell us a little bit about yourself and the work that you do here at the SEI? Let's start with Kevin.
All right. So I'm Kevin Pitstick. So I've been working in software and defense for about 15 years. The last 10 years, I've been at the SEI. I'm actually coming up on my 10-year anniversary here. So my expertise and sort of interest areas, they span a lot of things: edge computing, microservice architectures, containerization, related to what we'll be talking about today. And also communication protocols. When I first started, it was very heavy in kind of the edge computing R&D prototyping. I also did some projects in the realm of video summarization, AI/ML for the edge. I've done some architecture guidance, design reviews, and then recently, and what we'll be talking about today, I've been working on automated tools to help with best practices for containers.
That sounds great. Li-Han. What about you, Li-Han?
All right. My name is Li-Han Zhan. I have extensive experience in public software repository mining and containerization. One of the projects that I worked at the SEI is analyzing the impact of using software design patterning in a large code base. And another one that I worked on recently was drift monitoring of machine learning model to enhance the assurance of models. And recently, I've been working on Vessel, which is an automated tool for increasing container reproducibility.
That's great. That's a lot of interesting stuff. And as usual, it's always a pleasure to work with both of you. So, Kevin, let me start with a question for you. So what is the problem that your work addresses? What challenges are you seeing in container reproducibility these days?
All right. So first, I'd like to start with kind of a definition of what we call reproducible builds, which is the topic for the project. Basically, the idea with reproducible builds is that when software is built, there's some sort of input, and if a build is reproducible, you want to see the same output on the other end. And so in the context of container images, usually the input is something like the Docker file, there's the build context, all the files in, like, let's say your Git repository, potentially build arguments or environment variables that get passed in. And so the problem really lies with that most software that's built today is just not reproducible. There's a variety of factors. We'll talk about a few of them, things like timestamps, random numbers, randomly generated UUIDs, external dependencies that are always changing from package managers. And so realistically, when you build, even though containers are designed to be, a self-isolated piece of functionality that you can move from place to place, every time you build it, if you look at the checksum of the container image, it's going to be different. And so this poses a problem because, you build a container and you can't really verify if, when you build it again, if those differences are just trivial noise or if, something malicious has made its way into that container.
Right. So let me try to put your work into context. So according to your research review presentation, and we'll have a link to that presentation in the transcript, the 2020 SolarWinds hack involved malware targeting the software build process. Can you explain how reproducible builds would have prevented this attack?
Yeah, so that was a pretty big deal when that happened. Basically, so the the gist is that hackers, they breached the SolarWinds internal network. And so what they did is they got some malware called Sunspot installed on the build server that was building one of their products. And the whole goal of this malware was to watch for build commands to be sent. And so when it would see a build command being sent, then it would change some source code files that were being built. And that would insert whatever malicious attack into the application as necessary. And then as soon as that build was done, it would remove those changes from the source code. So it really was only visible while the build was actually happening. And a lot of times, when people are looking at, verifying their build process, you look and make sure that your source code is very secure. You make sure that changes aren't happening there. It's also very popular to put signatures on your final, executable binary to verify that that's not tampered with. But in this particular attack, neither of those things actually would have helped detect this. It really wasn't until they saw some unusual behavior happening from the application after it had already been built and distributed across the world that they realized that something odd had happened. And so this is a case where, with a reproducible build, if you imagine a situation where you had two different independent organizations, let's say within SolarWinds, one of them was actually infected with that malware. The other one is isolated, separate, not infected with the malware. If there was a reproducible build, they built their software 2 times and then were able to compare them and look for differences, this would have been a big red flag that would have shown up. And so, that's basically what happened and what we're hoping to prevent going forward.
Right. So, Lihan, you are one of the main developers on the tool that implements the process that you guys created. The tool is called Vessel. So, when you started working on Vessel, were there other tools that already did what Vessel does? Did you build on those tools? What are things that you had to create because they didn't exist, for example?
Sure. So when we started working on Vessel, there was no tool for comparing container images. We did some research and we discovered a reproducible build project called Diffoscope. Diffoscope is capable of comparing files, archives, as well as directory, but it's not built for containers specifically. So we ended up using it as part of our Vessel tool to compare and finalize image file system. And we also developed customized parser to convert Diffoscope output back to Vessel tool format. And another tool that's worth mentioning is Hadolin, which is a linter for Docker files specifically. And right now we are using it to identify and find reproducibility issues before the containers are even built. And in our recent research, we discovered a tool called DiffOCI, which is a newly released tool on GitHub, which is capable of comparing container images. However, that tool is only capable of comparing images at the metadata level as well as the manifest level. But Vessel focuses on comparing the container images at the finalized file system level. So those are the current tool, which still makes Vessel one of its kind as far as the current industry.
Right, so it seems like a lot more comprehensive, I should say.
Correct.
So can you walk us through a scenario of how someone would use Vessel? So from what I understand, you could use a Vessel to get a comparison of container builds, and then you could also customize it so that results are relevant to like an organization's containers. Is that correct?
That's correct. And to walk you through the different steps of how a user will typically use Vessel. So, for instance, a user will try to compare 2 container images built from the same Docker file. And our diff tool comes with pre-built set of flags to capture, trivial reproducibility issues such as timestamp. And then after the first try, the user will be able to see a lot of other unknown issues and most of them are project specifically related. For example, if the user is trying to build a Java application in his Docker file, then he will have a lot of Java specific reproducibility issues, right? And from that point, the user has the freedom to say add their own customized flags to capture those Java related issues based on file path and also the file type or regex format, right? And once he does that, because our Vessel tool is very easy to be containerized and embedded into the user pipeline, he can easily embed Vessel into his CI pipeline,
right.
And after every container build, he will be able to identify the number of reproducibility issues from there, and sort of a very automated process. And also another thing that I would like to mention is originally the intended use for Vessel was verifying the reproducibility of a Docker file, right? But it can also be used to capture the amount of differences between two releases of a container build. For instance, if you make a small change between your two releases, but you are seeing a large number of reproducibility issues, then you know something went wrong. Right? And vice versa, if you made a lot of changes, but you are only seeing a small amount of reproducibility issues, then it will be time for you to start thinking what went wrong, and then allows you to trace back to the development life cycle and identify the issues.
So that's very useful. So because what it means is that you've designed the tool such that it can fit into your own software development pipeline. So that's great. Okay, so given how comprehensive and how thorough the work has been, Kevin, it's not surprising that it's taken 2 years to get to where you are today. Can you break down what your approach has been in your pipeline?
Sure, of course. Yeah. So at the very start, after we had proposed the project and got funding, we took about a couple weeks, I'd say, to really delve into the existing work in reproducibility a little bit deeper, to try to understand what are these reproducibility issues and failures that would apply to containers. Some of the sources we looked at, there's Reproducible Builds Project, which we talked about. They have a lot of great tools, Diffoscope, a number of other ones as well. There's existing tools out there that do Dockerfile analysis or Dockerfile linting. Lihan mentioned Hadalint was one of them. And then there's a whole slew of papers that are looking at the Dockerfile ecosystem, whether on GitHub or elsewhere, and doing analysis of what kinds of just issues in general that they see, how often Docker files build or fail to build. One of the things we saw there is that if you just take all the Docker files off of GitHub and try to build all of them, a large portion of them just fail to build. And then there's, of course, trusty specification documentation. So the Open Container Initiative, OCI, is the container specification that governs, how the Docker containers are put together. So we looked through that as well as the Dockerfile specification to try to really get a grasp on, the lay of the land. So then after that, we started to look at prototyping this diff tool, a very basic version that would allow us to do the comparison of files within the container. And also needed to be able to manipulate container images, so pull them, unpack them, really, tear them apart so that you could compare two containers side by side. So we created the prototype Vessel diff tool. Then after that, we started to build some examples of different Docker files that were really doing isolated reproducibility issues. So from that initial list of issues and failures we were seeing from literature, we said, okay, we're going to try to write a Docker file that is 100% reproducible except for this one single issue, and then we could see how our diff tool performs on it and could account for that. So after that, then we said, okay, now we need to go out and go to GitHub. Let's get the real deal. Let's look at what real container images and Docker files are out in the wild and see what kinds of issues we could see with that. So this was an interesting process because there's a lot of a lot of toy projects. There's a lot of things out there that aren't the best examples. So we definitely went down the rabbit hole of trying to create a good representative set of open source Docker files. So filtering on things like the number of stars that the project has, making sure that the project was last modified in the last year or two, looking at number of commit hashes. So if it's just a single commit and it was just thrown up there, it's probably not actively being used. So we created this set, and also the other cases, in order for us to do our testing, we have to be able to build the container image. So we would gather, a whole bunch of images or a whole bunch of Docker files and identify repositories, and then we would go through and build, and somewhere 20-30% of them would actually build. So that was sort of representative of some of the other literature we'd seen. So after that, we have a prototype tool. We've got a representative data set. We looked at improving our diff tool identification. So now we had a whole bunch of failures within these builds that we could look at, and so we started to improve the flags that our diff tool was getting out of these with the reports. And then really from there, it was an iteration process of going back and forth between the data set, evolving our model of reproducibility, adding new fields in. And that kind of brings us to today, where our main focus right now is trying to optimize that diff process. So one of the things we ran into is the more representative the file or the Docker containers we're analyzing, we would see very long diff times. And part of it is, you just have, the more representative container images, they just have so many files, and sometimes you get, a large number of differences. And so one thing that Diffoscope buys us is it does a very in-depth analysis of any change it sees, but that also can take a while. Right. And so we're looking at ways to speed up the process, or potentially, circumvent certain comparisons that, might be less relevant, perhaps like create a fast mode. But yeah.
Wow. So Lihan, after hearing about the process, after hearing about what container reproducibility is and why it's so important, I think the audience is dying to see where they can find this Vessel tool. So where can people find the tool today, and how can they download it?
For sure. So today you can find a Vessel repo under CMU SEI in GitHub, and releases come with pre-built Docker images with all required dependencies pre-packaged. Right. So it's very easy to install and run it and test things out. And during the process, if you ever encounter any issues or found a bug, feel free to open an issue on GitHub, and we will get to it as soon as we can.
Oh, that's great, because you're going to be getting direct feedback from users. So, correct. Kevin, let's see that Vessel sees wide adoption because it's a super awesome tool. So how would this change things for software developers? Like, why is container reproducibility so important, especially for organizations like the Department of Defense?
So as sort of mentioned, there's not really too many tools out there that would help developers with this reproducibility. And so, if you were a software developer today, even if you wanted to make your containers reproducible, you'd be kind of in the Wild West of trying to track down all these differences. And so our hope kind of for the software developer people is that they have a sort of an internal or conceptual model of all the things that they could be, I don't say doing wrong, but things that they could be introducing changes in their container images so they're not reproducible. But then also giving them the tools that they can investigate those issues and potentially fix those. So that's what we're hoping to change for the software developers. Now, as far as, if you have, your organization is trying to adhere to certain security guidelines. So there's at least one framework, SALSA, SLSA, that in order to get to level 4 certification for that, you either have to have a reproducible build or you need to describe why your build is not reproducible. So this really gives developers a tool to help achieve those higher levels of certification. And then, going back to the question of, why is this important? I like to think about it in terms of the conceptual model of zero trust, where There's a lot that zero trust encompasses, but the gist that I like to think about is that you treat every step of the supply chain process as being untrusted. Mm-hmm. And so, we had talked about the SolarWinds attack earlier. Even if your source code you think is trusted, and even if you think the output binary is trusted and can't be tampered with, there's still that build process. And so you need to treat that as something that's untrusted. And so, if you look at the DoD, obviously very security-focused organization. Right. It's not the only organization. There's a lot of other organizations that do safety-critical work. But really, if they're striving for reproducibility, and maybe not every project within the DoD needs that full level of reproducibility, but for those who need it, mm-hmm. We want to ease their ability to get there so that they can really secure that supply chain and every step of the supply chain. And then hopefully those organizations who maybe haven't thought about it, or maybe haven't decided that the level of effort required to do it is worth it, mm-hmm.
It
might ease that barrier for them. So.
Right. Wow. Okay, that's all great stuff. I can't let you leave without telling me what you guys are working on next. So next time we bring in for a podcast, what are you going to talk about?
All right. So talking on sort of the vessel tool specifically, we talked a little bit about some of the optimization phase for the diff tool we're working on now. There's another aspect that isn't released yet. Hopefully will be coming in the future, where we're looking at Docker file linting and repair as a way to look at addressing the reproducibility problem more on, let's say, I guess the front end of the build process. So before the build even happens, there are issues that we can just analyze the Docker file and build context to see, what might go wrong. And so, it's really kind of taking that holistic multi-prong approach where we're analyzing before the build process and after the build process. And we think that those two could work in concert together very well to get a full, view of the reproducibility of the container. And I guess one thing I wanted to say as we kind of, talk about going forward, when a lot of times when you talk about the definition of reproducibility, people focus on a bitwise reproducibility, where when you create, and in this case it would be if you have one container and you'd say you do a checksum of everything in the container, and you do another one, you would expect those to match. I think that maybe should not always be the goal, and that instead we should be striving more toward, 100% explainability, so that we know that differences will occur, such as timestamps. Time is always moving. There have been some approaches to fake the time so that, those timestamps do match, but then that could potentially lead to other problems where you are reporting that your container was built, 20, 30 years ago. But in actuality, a lot of those timestamps, you would expect those to change. And it really comes down to, if you can explain every difference within your container to a reasonable degree, then it becomes a task of risk acceptance. Right. You say, yes, these are close enough, and we've identified every potential issue that we're happy moving forward.
Well, that's great.
And on my end, I'm also planning to focus on the engineering aspect of the tool. As Kevin mentioned earlier, I'm going to attempt to make the diff tool faster, potentially add a fast mode to make the tool more usable in a CI pipeline. And also we are going to test the effectiveness of our repair process and try to reduce the number of reproducibility issues prior to the build process of container.
Well, sounds great. Thank you, Lihan. Thank you, Kevin, for your time and for being here with us. For our audience, we will include links in the transcript to resources mentioned during this podcast, including the blog post on this topic. Finally, a reminder to our audience that our podcasts are available everywhere you find podcasts, including SoundCloud, Spotify, and Apple Podcasts, and the SEI's YouTube channel. If you like what you see and hear today, give us a thumbs up. Thanks again for joining us.
Thanks for joining us. This episode is available where you download podcasts, including SoundCloud, TuneIn Radio, and Apple Podcasts. It is also available on the SEI website at sei.cmu.edu/podcasts and the SEI's YouTube channel. This copyrighted work is made available through the Software Engineering Institute, a federally funded research and development center sponsored by the U.S. Department of Defense. For more information about the SEI and this work, please visit www.sei.cmu.edu. As always, if you have any questions, please don't hesitate to email us at info@sei.cmu.edu. Thank you.